This is module 5.2, and we're going to be talking about integrating network models with CompuCell. And if we have time, we're going to talk a little bit about steering panels, which you've seen a few times, not in a lot of detail. And our goal here is to try to build the delta notch model of juxtacrine cell signaling. As always, I need to remind you that this lecture is live streamed and recorded for future viewing publicly, and I want to thank our funding sources from the NIH and NSF. So we're going to talk about the basic syntax for integrating antimony models with CC3D through Python. We're going to talk about how to load, time step antimony models. I'm going to mention that you can delete and copy antimony models, although I'm not going to show you how to do it in detail. And I'm going to show you how to read and write values between CompuCell and antimony, which is actually fairly straightforward. We're going to do one little exercise on that. I'm going to give you a few thoughts about how to develop complex models, and then we're going to jump into building the delta notch model. Again, we're going to be using, to begin with, the code that we were just working with. And if you want more detail on this, I will also share a link to my videos of my network modeling course, which cover the content of the previous lecture in about 40 hours of lectures rather than an hour and a half. Again, I really strongly recommend that textbook of Herbert, the Antimony Tellurium cheat sheet, is very helpful for the basics. There's this nice systems biology introductory pathway modeling of Herbert's, very good textbook. There are many other good textbooks. He has this great online resource as well. And so to learn more, please go there. In 3 hours, we can only begin to scratch the surface of network models and network model CompuCell integration. But I want to give you the basic tools so you can get started to learn on your own. Okay, from last time, the nice thing about antimony is people are finding out the not nice thing about antimony is it's unforgiving of syntax errors, but most programming languages are unforgiving of syntax errors. The nice thing about antimony is it's very simple. You have triple quotes to define a string which contains your model. Inside the string, double slash or hash are comments. Semicolon is the delimiter. Colon names a law. Chemical reactions are the fundamental components of antimony. You don't need to name them. J1 names the law, but you don't need to name things. X dash caret Y semicolon B times X semicolon, rate law. Of course, B times X could be replaced with something more complicated like a Hill function or something with sines and cosines in it. The reaction X times Y could be something fancier like 3A plus 5B goes to A plus 2C plus 9D. You could write things that are pretty sophisticated. In earlier versions of antimony, the stoichiometric coefficients 3 and 5, for example, had to be numbers. In later versions of antimony, they can actually be variables, which can be quite helpful. But you'll have to look at the antimony manuals for the syntax for making them variables. You can write ODEs directly. T prime equals beta times T times V. That's equivalent to writing nothing goes to T, semicolon beta times T times V. That's all the syntax we need for now. CompuCell, TwidIt, and the manuals have slightly awkward syntax because of the history. When we started out supporting network modeling in CompuCell, we supported network models written in a different language called SBML. SBML is a markup language. It is used mainly as an interchange language. It's really not designed to be read by people. It's designed to be read by computers. But because of that, a lot of modules in CompuCell, which are dealing with networks generically, are named SBML something. And so when you see the word SBML in general in CompuCell, it just means network. And I realize that that could be confusing, just the way the word temperature isn't really a temperature. SBML really means network. There is a particular code snippet menu in Twit. If you pull down the Python menu, you select SBML solver. It really should say network solver. You'll get a lot of options. Add antimony model to cell, add SBML model to cell, add cell ML model. SBML, cell ML, and antimony are all different languages for expressing network models. They all evaluate to the same thing. Time step SBML model. Should really say time step network model. And so for most of these things, except where it says load SBML model, add SBML model, every place else it says SBML, it should be network. So please be aware that when we use the word SBML here, we really mean network. We're not going to do any actual SBML coding today, but it's supported. When we load models into CompuCell, there are actually a number of scopes for model loading. You can load a model into every cell all at once. So every cell has the same model. You can load models into cells one at a time by cell ID. You can load models by cell type to all cells of a given type. And you can load a free-floating model that runs in the background, which is what we were doing just now. While the load scope has by type all cells by individual cells, in fact, there are only two scopes for models when they're actually implemented. Each model within each cell is independent, no matter how you load it. And free-floating models are free-floating models. You can have multiple models inside each cell, and those models can have different timescales and be solved with different integrators. And you can also have multiple models in the background in free-floating models. So you have a lot of flexibility that way. We do not have the adaptive time stepping that was asked about earlier. It'd be nice to have that, but that's not available. But you can have different models which run on different timescales within the same cell or between different cells. When you're referencing SBML models, and free-floating model means simply that it's not connected to any particular cell. It's a model that runs, a network model that runs inside of the whole simulation. It's a model not related to an agent, as Michael says. The name of the background model is self.sbml.model. And again, you can have multiple ones of those. And a model loaded into a cell is cell.sbml.model. So the syntax is pretty straightforward. Self.sbml.model is a model that runs simply in the system as a whole. Cell.sbml.model is a model that runs inside an individual cell agent. Somebody always asks, can you load SBML models into fields? And the answer is no. Might be nice, but you can't. So we spent the last lecture talking about antimony syntax with only a tiny bit of how we were supporting it in CompuCell. Today we're going to talk about, well, in this lecture, we're going to talk about how to run control antimony in CC3D. The integration is through Python. As I mentioned, we can load antimony models just for the simulation as a whole, or into individual cells. All antimony parameters and variables show up as CC3D dictionary entries. So if you're familiar with dictionary entries, every time you generate an antimony model, it will generate a dictionary entry. You're going to have to time step those models from CC3D Python. And for each model class, you're going to have to determine whether you use the deterministic reaction kinetic model solver, the ODE solver, or the Gillespie solver. And again, you're going to be using the code snippets, SBML solver, and you're going to be doing add antimony model. And you can add, say, add antimony model to cell ID, cell type, and so on. Okay. If we look at the code that we were working with, this is actually going back to a slightly different version of the code, but it's very similar. We're going to see that in the Python, there are a couple of blocks. And because the text is small, I'm not going to do a split screen. It gets to be too small to read. At the beginning of our code, we will see the model definition. And model is simply the name of a string. It could be my model, ATP model, cell differentiation model, any valid Python variable name. Triple quotes, string defining the model, and a triple quotes. We had a statement variables equals in our code, A colon red, B colon blue. That's actually pretty specific to the plotting that we were doing just now. And then if you look down in line 30, you will see a line self.add free floating antimony. And then model string equals model name equals model, step size equals 1. And then if you jump down to line 48 in the step function, you'll see self.timestep underscore SBML, which time steps all the models in the system. You'll notice in line 30, I can define this time step to be whatever I want, and therefore the time step that is used in line 48 will be what was defined in line 30. Abhishek, go ahead.
Yeah, so what is the significance of lines 18 and 19?
Those are antimony events, which we didn't talk about. It's simply an example of what's possible here. Events are typically in CompuCell. We're going to do events in the CompuCell Python, but antimony allows you to have events that happen. For example, suppose the cell that you introduce a drug at a given time, or thresholds where the behavior of the system changes. Those can be defined inside of antimony as well. And that's an example of an event.
Oh,
This is
thank you.
this is boilerplate code to illustrate the components, but that's a good question. I mentioned events very briefly, but we didn't do them in this class. Okay. So again, if we're going to build a CompuCell model with antimony, the first thing we need to do is to define the antimony model specification. We could put the antimony model specification in a string, the way we're going to do it. It could live in a file. We can import it from a file also. We could write our model specification in systems biology markup language, SBML, in CellML, or in this stochastic Boolean network modeling language called MabBoss, which TJ will talk about this afternoon. So you have a lot of options for your model spec here. We're only going to do antimony because it's the simplest one to learn. But if you like SBML and you like to use Copazi or something to do your network models, that's possible. Okay. The next thing we need to do is to load the model specification into CC3D. Here we have that line 30, add free-floating antimony model. And let's look at the arguments of this. Add free-floating antimony model loads a single copy of the model specified in model string. And here we've set the step size to 1. It says 1 unit of antimony time is equal to 1 unit of CompuCell Monte Carlo step. again, once you've loaded it, whether the model is specified in antimony, CellML, or SBML, it's always called an SBML model, which can be a little bit confusing. And again, this is history. When we created these functions, we only had SBML, and that's how they got their names. Okay. In the step function, we will have to time step our model. And again, that's a very simple call, self.timestep SBML. You want to be careful in your step function not to put that time step inside of a loop, because you really only want to call it once per Monte Carlo step. So if this antimony model has a variable A and it's assigned to a cell, the cell dictionary adds an entry called A. Almost, but not quite. There's a special dictionary for the SBML models, and I'll show you that in just a second. In general, the defaults that the integrators use are pretty good. Occasionally, you can get integration errors because you write a stiff model system. And so there are a variety of integrator settings, which I am not going to go into today. You can look them up in the manuals for libRoadrunner and Tellurium. Set SBML integrator global options. There is a convergence rules, relative or absolute. You can define the tolerance, the error tolerance for the integrators, whether you are trying to run stiff equations or not, and then those options can be set. Some of these slow down the simulation, some don't. And again, there's a lot of magic about how these integrators work, which I can't talk about today. I have to refer you to the manuals. In general, the default settings are pretty good. And for everything we're going to do today, you're not going to have to change the default settings. Here is how we are going to read and write antimony variables and parameters. As I mentioned, these exist as dictionary entries. However, they are special dictionaries because you could have multiple SBML models, and therefore inside of a single cell, and therefore you need to be able to reference which variable belongs to which model, because you could have the variable A in two different models, and it's a fundamentally different value. And so self.sbml.model square bracket key name gives you the value of the antimony variable or parameter with that name. So, excuse me, if I have a global SBML model, self.sbml.model square bracket A will read the value of A from the antimony model. I can read or write to it as I choose. I don't have to do anything special. If I say self.sbml.model square bracket K1 equals new value, I've overwritten the value of K1. So I don't have to do any getting and putting of values to be able to see what they are. The one thing that I might have to do is if I have a tracking field, I might have to copy from the SBML model dictionary to the cell dictionary to create the tracking field. Okay. This is just a summary again. If you don't remember how to do this, set SBML state for free-floating model, set SBML state for individual model in the code snippets will give you the syntax cell.sbml model, square bracket variable or parameter name for a model loaded into a cell, self.sbml.model variable name for a free-floating model. The rate laws, the rates where you declare the name of a reaction and get the reaction rate, For example, if I called a reaction J1, that can be read, but it cannot be overwritten because it is determined by the simulation of the network itself. So let's actually now use that. Let's take the code that you just had from the last exercise. If you don't have it, download 5_2_1 Antimony in Python, if you prefer, is the completed code. You'll want to undo the Gillespie solver. Doesn't do any harm to have it there, but the example I'm having doesn't use the Gillespie solver. So you take out that 1, Gillespie that we added in line 31. And we're going to add an overwrite where we change the value of a rate constant in the simulator. So here was my A goes to B, B goes to C, C goes to D, D goes to A chemical equilibrium model. And I've got Ka, Kb, Kc, Kd all equal to 1. And now in my start function, I'm going to add that model. And then I'm going to add a line 32, which says self.sbml.model, square bracket, quote, Ka, end quote, square bracket, equals 2. What is that going to do? That is going to overwrite the value of Ka from 1 to 2. Why don't you see if you can make that change? See what happens. So now I am taking the initially specified model template that was in my string, and I'm overwriting it with a new value in CompuCell. And so that's pretty powerful because I can have a template model that I define, and then I say, well, in this cell, the rate is this. In this cell, the concentration initially is this. And so I can use a template and then change the template to correspond to the situation in each cell separately. If you've got that worked out and you want to get ahead, try changing the values of Kb or Kc, or instead of making it 2, make it 10. Or try changing the initial conditions. Why don't people try that and see if that runs for you, okay? I'll give people a minute to do that. You're adding 1 line of code, and it's okay if you left the Gillespie thing turned on. It's not going to change things very much. Jupyter already has it going. This is a case where maybe saving a screenshot with the old value would be interesting so you can compare the results. In this case, we're changing the value in the start function, but we might very well, and most often, we will change values also in the step functions. In particular, we'll read the values because we'll change the behaviors of the cells based on the levels of the chemical species in the network in the step function. So you say if we change A, B, and C in the stepables, in the step function. No, well, it depends. Here we're going to do it at the beginning just to see what it does. But in general, depending on what we're trying to do, we might change the initial conditions of the model, which is what we're doing here. Or we might say, gee, the amount of this chemical has changed, and therefore in the step function, we change the amount of the chemical. Or the rate of this has changed, therefore we change the rate in the step function. So we're very often going to read and write in the step functions. The reference to the dictionary entry works just as well in the step function or start function. Good question.
I'm still trying to figure out why we would change it in CC3D instead of in the antimony code. It's because we can, from what I heard, it's because we can change the value for a specific cell or cell type directly, right? Instead of what?
Well, suppose that I have a situation in which I put a drug into the environment of the cells. Suppose I'm doing a cancer simulation, and I now put a chemical into the environment, a chemotherapeutic, at a particular time in the simulation. That chemical is diffusing in the environment, and the cell is taking up an amount of the chemical. I then take up that amount from the chemical field, and the cell then has to pass that new amount of that chemotherapeutic to the antimony model, because the antimony model then might regulate, for example, cell apoptosis based on the concentration of that chemical. And that would be done on a cell-by-cell basis. So anytime I'm going to have interactions between cells, I'm going to have to be able to do this in the CompuCell layer. One of the problems with antimony and SBML was that when they were created, they never thought there was more than one cell in the world. So there are no features for coupling multiple cell models together in SBML.
Yeah. Okay. They're like, I'm thinking of the event triggers, but that would still be within one cell.
Right.
Yeah.
So I have to tell it what the outside world is doing. I mean, some events might happen naturally. If the concentration inside the cell gets bigger than such and such, the cell goes into apoptosis. That might be done inside the network. But nevertheless, if I'm interacting with the environment, I have to be able to pass those environmental signals to the cell network. So that has to be done at the CompuCell layer. And the case of the delta notch is particularly good that way. It's an extremely simple model, but it cannot be realized inside a single cell. It obligatorily needs 2 cells or more. So again, if you've got this working already, you can try playing with other values. So in general, what's called a boundary species. I did not talk about setting boundary species in antimony. If you there's a symbol called a $sign, which is a $sign. I don't know why that was adopted in antimony. If you put a $sign in front of in principle a variable like a, that locks the value of a and means it can't change. And that's defined as a boundary species. I tend not to use that very much. Herbert likes it a lot. And so if you want to see how to do boundary species definitions in antimony, I'd refer you back to Herbert's great online textbook that read the docs that I sent the link for. It's possible to do that. Somebody says you can also set as a parameter on a variable. There are a lot of ways you can implement fixed values. Okay. So here's how to do that. To read the value of A at a given time, we'd say something like A equals self.sbml.model, square bracket, quote, A, close quote. Again, remember that things are case sensitive. It's super easy to type K under uppercase A, K instead of a lowercase k, for example, and then you'll get errors. And again, antimony tends to fail by crashing rather than by giving you an informative error. And so follow those debug steps of commenting things out, uncommenting in a systematic way if you have antimony errors. Okay. And now, if we had more time, I would do a bunch of simple exercises to play with antimony, but we have a limited amount of time today. Again, I certainly encourage people to explore all these additional antimony features. Antimony has random number generators, it has events, it has piecewise linear functions, a lot of neat things, all of which are really useful, but which, again, I'm focusing on just the fewest possible steps that we need to build an integrated model. I'm not going to be able to go into the fancy stuff here. I want to give you enough that you can learn on your own afterwards. So we've seen this immunogenesis simulation many times. Inside each one of these cells is an oscillating signaling and gene regulatory network, a rather complicated one. It's actually 3 separate oscillators that are coupled to each other. Having just said you should always write the networks, here I've got the ODEs, so I violated my own rule. Every one of these cells is running this network. That network is happening independently at every cell. Those cells are interacting with each other through delta notch and other signaling on their membranes. There's also a different or a rule-based network that is reading the states of all of these things, reading the level of extracellular concentration of this diffusing molecule, in this case, FGF8. When the level of FGF8 goes below a threshold, it reads the phase of these oscillators and then has the cells differentiate in response to that phase, change their cell adhesion properties, and change their migration properties, and that leads to the physical formation of the somites. What's interesting about this is that we start out with a continuous strip of tissue where every cell is the same, and it breaks up into these stripes of different cell types that then reorganize into spatially separated blobs. And that segmentation process, semitogenesis, is one of the fundamental steps in developmental biology. Another classic example of this is actually the Tyson cell cycle model that I mentioned. This one happened to have been loaded. This is a very old model. It was loaded from SBML. I'm running that cell cycle model inside each cell. It's controlling the growth and differentiation, sorry, the growth and division of each cell. And the color here is representing one of the cyclins in that model. So when I'm going to do CC3D integration, it's more or less what I've said before. We're going to specify the model, the network model. We could have multiple ones. Today we're only going to have one. We're going to use the same network model in all cells. We're going to load that network model into the individual cells in this case. It's more interesting than the whole network one. We're going to time step that network model. It is absolutely possible to get oscillatory dynamics, not in the specific example that we did before, but if you're interested in oscillators, we can definitely point you in the direction of significant biochemical oscillators. Cell cycle is a classic oscillator. Circadian rhythms are classical oscillators. Calcium waves. I have the whole calcium wave demonstration tutorial implemented. We're not going to have time to do it this year, but it was done in module 8.4 last year. And so if there was somebody here who was interested in calcium wave dynamics, that whole network model and all of the examples are available to you from last year's module 8.4. Again, we're going to define our antimony model. We can have multiple models in a single cell. We have to remember that if we're going to have multiple models, we have to give them different names. And we also have to keep track of conversion of antimony time to SBML time, CompuCell time. Again, our basic syntax will be self.add antimony model to cell, and then we can read from model string. We could also read from a file. I'll show that to you in a second. The name of the file, model name. That name will be different. If we load multiple models into the same cell, each one has to have a distinct name, which cell we're going to load it into, and the step size. Notice that we could use, in fact, a different step size for the same model inside different cells, although I'm not sure whether that would be very meaningful. Okay, so here would be an example. I have Glazier model steppables. I have SBML step size. Sorry, this is coming back to this. It's very useful to create a global parameter which reminds me what the SBML step size is. Days to Monte Carlo steps, minutes to Monte Carlo steps, seconds to Monte Carlo steps. Both antimony and CompuCell don't automatically have units for time. And so you have to more or less have in a comment what the time units are, but it's very useful to define in your simulation a statement of what those time units conversions are. Okay. We didn't talk about this yet, but but I think maybe one of the lectures actually mentioned this. I think Peter's lecture, but it may have gone by a little bit fast. If you put variable name or parameters in the program before the class definitions. Those are available for reading everywhere in all of the classes. They're not available for writing. So you can read the value, but not write it. So it's really a parameter. I find it very useful to have some conversion factors, seconds to Monte Carlo steps, days to Monte Carlo steps, and so on, predefined. We should probably have them predefined with reserved names in the Python. At the moment, you have to do that for yourself. Okay. The next thing that we're going to do, and this also goes in the header before all of the class definitions, is we define our model strings. And it's good practice to put that after the conversion factors and before the steppable class. Okay. We have a bunch of different loaders, and I'm just going to name them. I'm not going to go through all the details. You can add antimony models to a single cell. You see cell equals cell here. You can add antimony models to cells by the cell ID. And here I can have IDs equals and then a list, cell number 1, cell number 15, cell number 23. I can add antimony model to all cells of a given type, model name, cell types equals, and then a list of all the cell types, self dot cancer cell, self dot somatic cell. And I can add the free-floating antimony model to the whole system. Model name here specifies how to refer to this model from CC3D Python. Step size is the time conversion. If I want to read from a file, instead of saying model string equals model, I'd say model file equals, and then whatever the path name is. If I want to use the stochastic Gillespie solver, I would say comma integrator equals Gillespie. The Twidit code snippets give you all of these options, so I strongly recommend using this. We're not going to use this very much, but you can define overwrites in the load. I can define a dictionary, which I could call initial conditions, and then I could say initial conditions S1 equals such and such, initial conditions S2 equals such and such. And if I put in initial conditions equals initial conditions in the loader, that will overwrite the initial values of those whatever parameters and variables I set there, just the way I did by hand in that first example. Again, that's in the code snippets if you forget the syntax. In the step function, we use self.timestep SPML, and that time steps every model. We don't have the ability to say we're going to time step this one and this one. Might be nice, but we can use those time settings, those time step settings within the loads to do different rates of evaluation. And again, we had that option for the parameter set for the integrator settings if we wanted to. Some hints when you're trying to do debugging, and these will probably make more sense for you once you've started doing it. The network integrators can crash for a whole variety of reasons. Often you'll see something which will say CVODE error, which is a convergence error. If you see that, usually it means there's a mistake. For example, a divide by 0 in a rate law. You can't have an infinite rate. It's easy to get one by mistake. Real rates don't go to infinity. On the other hand, there are situations where real rates can be quite fast, and if the time step of your Monte Carlo steps is minutes, and you're trying to simulate neural networks where there are oscillations on the periods of milliseconds, then you have to be careful about the time integration. So one way to do this is load the simulation and just do one step. If it crashes after one step, you almost certainly have a typo or a syntax error divide by 0. If it does run a step, keep doing single steps and see what happens. If it crashes, one thing you can do is make your step size 10 times smaller and see if it stops crashing or not. If it does crash, even when you make the step size very, very small, then there's a mistake in your antimony definition or in the variable or parameter assignments. That means it's a divide by 0 at the beginning. It's also possible that you used a reserved word as a variable parameter name. That can be an insidious error in antimony. If you've identified a divergent rate, ask the question, is that divergence what happens biologically, or is it something you can smooth out? A lot of times, if you have very rapid change of concentration chemically, for example, in an action potential, you can actually slow it down without changing the way the model behaves very much. If you really need very fast changes in your biochemical signals, then you have to reduce the step size by making the number of microsteps more. And you can do that. Those both slow down the simulation, but there's not much you can do about that. It's intrinsically the simulation is stiffer than you might like. It is possible. There was a question about dynamically changing the time steps. I said that there wasn't a simple way to do it, but it is possible to change those time steps as the simulation runs if you want to, but you have to do it by hand. And so you could change the step size or the number of microsteps per call to the SBML solvers each time you call them. That's not very elegant, but it's possible. Again, we have in the TWIDIT time step SBML models. That's a simple call that will paste in that time stepper. There's the add SBML model option here, which we have there. Okay. Again, I've said this before, to read or write a value from the SBML, cell.sbml.model name. Somebody asked, is that model name? Yes, it is. Model name, square bracket, name of the variable or parameter. Self.sbml model name, square bracket, name of the model or parameter. Okay. If you want to get the full set of all variables and parameters in a particular model, you can pull result equals self.sbml model name dot values, and that will dump the whole dictionary out. There's a question which is microsteps per time unit, which is how is this different from step size? When I call time step, it will take the SBML model forward. If the time step is 0.1, when I call the time step, it will time step the SBML model forward by 0.1 of its time units. But in the integrators, I can say when I am doing my integration, do I subdivide that 0.1 into 10 steps, substeps, 100 substeps, 1,000 substeps, 1,000,000 substeps? And so it's basically giving me the temporal resolution within the integrator. So maybe that wasn't clear. Ali asks, should the model names be unique for cells? No, you can use the same model. You should use the same model name for all cells if it's the same model. But suppose some cells have an ATP model and some cells have a WNT model and some cells have both. Then I would have to give the WNT model and the ATP model different names, because if I want to load two models into the same cell, the models have to have different names? Good question. You can copy SBML models, and when cells divide, the SBML models are copied automatically. You can copy models from one cell to another if you want. When you instantiate a new cell, not through cell division, but by creating a cell by hand, you might very well want to do that. When you have a cell differentiate, you might want to copy the model as well. It's possible to delete models from cells. You rarely need to do that, but it takes some compute time to run a model. And if you have a lot of dead cells present that aren't actually running the model, you can take the models out. Yes, when you delete a model, all of the variables associated with it disappear. So now I want to build up in our remaining time to the delta notch patterning exercise. If you can do this exercise, I think you mastered the basics of CompuCell antimony integration. And it's really a beautiful model. And it's also one that's virologically very, very significant. So delta notch is a juxtacrine signaling mechanism. It is a cross-inhibitory mechanism where cells signal to each other through a pair of molecules. And each cell tries to push down the value of that molecule on the opposing cell. And in the intestinal crypt, you already ran at the very beginning of the class, you ran that intestinal crypt simulation that ran a delta notch simulator inside of it, and you saw a speckled pattern arise. If I look in Drosophila inner ear, you see delta notch patterning for the hair cells. If I look in the eye of the Drosophila, I get delta notch patterning. If I look in zebrafish in the eye, the photoreceptors use delta notch patterning. Delta notch patterning is also critically important for blood vessel development. It's one of the key regulators of cell fate in developmental processes. Somebody asked, could we have different SBML models for the cells from pericentral to periportal? Absolutely. Whether you have different values of parameters for the same big model or you run different submodels for different cytochrome oxidases is a choice you'd have to make, but both are possible. I'm only going to be able to talk about delta notch in a very high level here. Lorenzo's an expert on delta notch modeling. His delta notch models are much more sophisticated than the one I'm going to do here. This is still a topic of current research. Okay, here's the basic delta notch concept. If I have delta on one cell, it binds to notch on the neighboring cell. The notch sends a signal that inhibits delta on the same cell and also inhibits specialization of the cell. So I have a cross inhibition between neighboring cells. If I have a high level of delta, that cell will tend to specialize and inhibit its neighbors from doing the opposite. And so high delta tends to be the differentiated state. Low delta is the less differentiated state. And you tend to get not a checkerboard where you have adjacent things, but you have high delta surrounded by here 6 low delta cells. Initially, cells will have both delta and notch on their surfaces, and then they'll tend to assume either a high delta fate or a high notch fate. It's a seesaw mechanism. Okay. The actual process involves a lot of steps. There is an extremely simplified version of this model due to Collier from 1996, and that's the one we're going to model here. In reality, the notch signal is mediated through the notch receptors actually cleaved. There's intracellular notch. There's movement of notch in the cell. We're going to neglect all of that. This very simple model recapitulates much of the behavior of delta notch, and not all of the biological complexity, but a lot of it. We're going to assume that active delta binding to active notch causes notch to inactivate delta. Inactive notch promotes active delta. And that's going to lead, I should really have more arrows, but to two ODEs. The level of delta inside my cell, active delta inside my cell, is inhibited by notch. If there's no notch, I'd get V times 1. So that means delta is pushed up. And delta decays. Minus delta is decay. Notch, on the other hand, the level of notch depends not on the level of delta in my cell, but on the level of delta in my neighboring cell. So d bar represents the average amount of delta, not on my cell, but on the amount of cell in my neighbors. Okay. So d bar is the signal of delta I'm getting from my neighboring cells. I don't care about how much delta I have in my own cell. That's a pretty harsh approximation, but it makes things simple. And again, notch decays. So delta in the absence of notch is produced and decays. In the presence of notch in my own cell, delta production is turned off. Notch is not turned on unless I have delta in my neighboring cell, and it decays. Got that?
How is delta active versus inactive? I thought it was just a ligand, which is either present or not present.
Right. So in reality, there are different states of delta, whether it's bound to notch or not bound to notch. And the same way, notch is activated or inactivated depending on whether it's bound or not. We're neglecting that. We're neglecting all of those complexities. A more complex model would have bound delta, non-bound delta, bound notch, non-bound notch, cleaved notch, intracellular notch, and so on.
So it's more of like a conformational state that enables binding.
So when delta binds to notch, we consider it active. So we're considering that the coupling between the delta and notch between the cells happens instantaneously. We're neglecting the kinetics of the binding. Again, this is a pretty harsh approximation, but it happens to reproduce the right patterns. That's why we're using it. I definitely would encourage people who are interested in the biology here to look at some of the beautiful delta notch models that have been published that are more sophisticated. For our purposes, we're doing the simplest thing that we can do that we can build in half an hour. And so I appreciate the question. Again, we would say that delta here is just, we're going to only have two numbers, the amount of active delta and the amount of active notch. That's all we have. And the parameter values are going to be a little bit strange. I would have scaled this differently if I had written the model, but I didn't do it. Okay, when we run this model, we start out here. This is not visualizing the notch concentration. We start out with all the cells having almost the same notch concentration. There's a little bit of random noise here. And we're going to see over time, some of the cells are going to have high levels of notch. Some of the cells are going to have low levels of notch. This region here, the cells are having a hard time making up their mind because they're getting conflicting signals. Depending on the spatial geometry, we might get a steady state or quasi-steady state situation, or we might see some cells switch periodically, not periodically, but at irregular times between the two states. Okay, here's some general comments on modeling. We're going to be building generally with CompuCell or any of these virtual tissue packages, very complex models. First, when you're going to build a complicated model, think carefully and write down the conceptual model. What are the things you're modeling? What are the processes? What are the interactions? What are the dynamics? What are the events? What are the initial and boundary conditions? If there are interventions at particular times, what are they? and write that out in as much detail as you can, and write down as carefully as you can what it is you want to get out of the model. What specific parameters do you want to, variables do you want to predict? What specific situations and perturbations do you want to predict? When you jump to coding, start by building the simplest possible executable submodel. Don't try to do it all at once. Usually that would be creating the initial cell configuration, just the layout of the cells, basic cell behaviors like volume and interactions like contact area. Just throw the cells up. Create the chemical fields. Don't have them do anything. And make sure that that submodel runs, doesn't crash, doesn't do something strange. Cells don't disappear on you. They don't fragment. The chemical fields don't blow up on you or disappear. And then at each time, each step of your model development, add one object class or mechanism at a time. And ideally, you should design your simulation so you can turn that off with a flag, for example, in case there's a problem. So you really want to design your model so that every submodel can run independently of everything else. Now, there's some things where it's not so easy to do that. A delta notch, the network model really has to run inside the cells because it has to couple between cells. But as much as possible, break your modeling into independent modules that you can add one at a time and turn off. Turning off is critical. After you add each component, run it, make sure the syntax is right so it doesn't crash, and then make sure that the simulation does what you expect. And do that in a very systematic way. People tend not to think enough before they start building models. They start writing code right away. Always a bad idea to write model code without having written a detailed specification of what you're trying to do. And then they try to write the whole simulation at once. We saw that with this kind of process with Sluka, where he added mechanisms one at a time, starting with something very simple. And we also saw that with Pedro when he was building the vascular tumor model. I mean, the avascular tumor model, where you add things one at a time. When you do that, you're much more likely to have success. So, for example, you might start out by defining your cell configuration. And then you might add chemical field and diffusion, but not have it coupled to the cells. And then you might have the cells take up the chemical and check that the concentration changes the right way, but not have it affect the cell behavior at all. Then you might have the cells grow. You might have the cells divide. Then you might add an intracellular network and not load it, just make sure it doesn't crash. Then load it in the cells, but don't have it do anything. Then load it in the cells and couple its behavior to the cells. But try to do these things stepwise so that if you've made a mistake, either syntactically or logically, you find it as soon as possible. Because once you build a very complex model, if you have a problem with it, doesn't do what you expect, and you haven't looked at the components separately, you can't look at the components separately, it's almost impossible to debug. Okay, so for building delta notch, we're going to create a small space full of cells. We're going to build the model in Antimony. We're going to add the Antimony to all cells. Each time step, we're going to loop over every cell, loop over cell neighbors. Remember, we were shown how to iterate over the physical neighbors of a cell. We're going to calculate that D bar by averaging D from the neighbors, set the value of D inside my cell, visualize the pattern of D and N. That's what we're going to do. If you want to try building this model on your own, that's great. I would recommend people download the model, the completed model, so that if you get stuck, we can go ahead and you have it to work with and you can do step by step. The model is exercises 5. This is actually should be, I'm sorry, it says this wasn't updated properly. This should say 5_2_2_ delta notch. I'm going to walk you through the steps we're going to go through quickly, and then I'll come back and we can do it together, and I'll let you do it, okay? So, step 1, you're going to create a 42 by 42 by 1 simulation domain, single type of cell. You're going to use volume local flex, contact energy. Use the uniform initializer to fill the simulation domain with cells of size 7. In the steppable file, in the start function, you're going to assign a target volume of 50 and a lambda volume of 2 to every cell. You're going to use periodic boundary conditions. You're going to write the antimony string corresponding to the ODEs for the delta notch model. You're going to load the antimony model into all cells and initialize the values of delta and notch on every cell from a uniform random distribution between 0.9 and 1. At each time step, so this is all in the start function. In the step function, you are going to calculate at each time step the average level of D surrounding each cell. You're going to update that D average value inside of the network model for that cell. And you're going to create an auxiliary field, this is actually before the start function, to display the values of delta and notch in each cell. Okay. Those are the steps. So step 1, create a 42 by 42 by 1 simulation domain, periodic boundary conditions. Use uniform initializer to fill the simulation with domain cells of domain size 7. Define a single type of cell, volume, local flex, contact energy. You'll need neighbor tracker because you're going over all the cells. And in the steppable start function, assign each cell a target volume of 50 and a lambda volume of 2. Okay. Why don't people try doing that and run it, see what you get. Use Wizard to do that. Neighbor tracker is one of the tick boxes in that last pane of Wizard. When you're setting the cell properties, it's in the last pane of Wizard. There's a set of trackers on the top right. So this is a good test to see if you remember how to use Wizard. You should have something that looks like this. You will have to edit uniform initializer to make box min and box max correspond to the whole size of the lattice. Change the size of the cells to 7. And then in the start function, add for cell and self.cell list. That'll give it, I think it'll give it to you automatically. Cell, but you'll need to type cell.target volume is 50, cell.lambda volume is 2. So you have to edit 1 line, 2 lines, 3 lines, 4 lines, 5 lines of code from what you get from Wizard. And this is the correct code to download if you want. Where is the contact energy? The contact energy is in the same frame that Kimberly pasted in at the end of the simulation, at the end of the Wizard settings. It's the tick box in that frame that asks you what the cell property should be. It's the very first tick box. It's called contact. It's okay to have the cells not fill the whole space, but for this one, you have to edit the uniform initializer. In principle, it's okay. It's interesting to have the cells not fill space. You get slightly different results. It's an interesting thing to play with when you have a free surface or not. If you wanted to fill the whole space, you have to edit line 4950 of the code, box min and box max to fill the space. It should pre-populate the start function with an iterator over cell and self.cell list. If not, go to CC3D Python, go to visit and visit all cells. And then you'll have to type cell.target volume equals 50, cell.lambda volume equals 2. The next thing you're going to do is at the beginning of your simulation, before the first class, you're going to put in your triple quotes. Remember how to write antimony models. You're going to write an antimony string corresponding to the ODEs. And remember the basic antimony syntax, J1 : dash, caret, X is equivalent to writing dx by dt equals rate law. So you'll write J1 colon D, nothing goes to D, dash caret D, semicolon, V times bracket 1 over 1 plus. Remember, exponentiation is caret, up caret for antimony, minus D. Okay. And you'll have to set the initial values. A is 0.01, B is 100, V equals 1, K equals H equals 2. So take a minute to type that. And you may need some extra parentheses to implement them. So you're going to have two rate laws. You're going to have to define values for V, B, H, A, initial values for N, D, and D average. And remember, D and D average are different variables. So you could call one D and one D AVE or something like that. Here's what I typed. Now, to save yourself some typing, you don't have to type the comments like reaction, species initialization parameters. You do have to type the J1, J2, DAV, and so on. So I'll give people a couple of minutes. You can figure out the syntax on your own. That's great. If you want to look here, that's good too. But you need to, everybody needs to put that in. I realize that's a little bit of typing. Make sure it runs after you've typed it. Don't want to, it's easy to have a syntax error. Actually, without parsing it, you're not going to know whether it runs or not. Please make sure it doesn't, typing the string doesn't crash things. Again, if you get behind, please use the completed exercise and follow the code along. If you get desperate, one thing you could do is if you have the downloaded code and you have your own code, you could cut and paste the model string from the downloaded code into your code. That saves you some typing. The model needs to go at near the beginning. If you look at the line numbers, that's a suggested place to put it. It goes in the Python stepables before the class definitions.
This is a newbie question. Why does it not go into the XML? What's the difference?
Well, in principle, you could put it in the XML if we had the features for that. But the XML, we don't have a way of parsing model strings. In other words, in principle, we could define a set of XML tags that say, define SBML model or antimony model in the XML. There wouldn't be any reason we couldn't do that, but it's not implemented that way. So, and Washa has put this in the start function. And you don't want to put this in the start function. It won't necessarily not work there, but it's probably not where you want it. It should go in the beginning of the simulation, after those initial loads, but before all of the class definitions and before the init. There's a question, does it care about extra spaces? The Antimony, unlike Python, doesn't care about indentation and spaces, no. The next thing we have to do is load that antimony model into all cells. And here it says of type A, but that's because, well, that was one way to do it. We load it into all cells. Here I loaded it by cell type, but in fact, we'll just load it into all cells. So go to SBML solver, do add antimony model. And here it says to cell types, but you could just load it into all cells. That SBML solver is going to paste in some verbose things. it will paste in model file equals and model string equals as options. You have to delete model file equals. You're not using it. And it'll also paste in this initial conditions option and integrator option. Get rid of those. What you want is text that looks like this. I called my cell type cell A, but if you gave your cells a different name, use whatever name you used. So whatever you named your XML model definition, if you typed here, I called my model string. I could have called it DN model. Whatever I typed in line 9 for the variable that holds the model string, use that here. Integrator defines whether you're using Gillespie or the ODE inner solver. And it allows you to set the parameter, the integration details, which we're not using. I am naming this model DN. This is the name I am choosing to give this model. Yes, one thing that can be a little bit confusing in these kinds of calls is model string is the thing I'm going to read. Model string here is the variable name which contains the information. So maybe it would be better to have model string 1 and model string 2 or something. Well, this has to be model string. That's exactly a reserved word. This is the variable name. There's a tendency when you're doing demonstration Python to keep those things being the same, but maybe it's confusing because they are actually different object types. Yes, when you call the model, you're going to use cell.spml.dn. Yes. .dn. This name is going to be the name of the model. The next thing that we have to do after we've loaded the model is we have to initialize the values of delta and notch inside of every cell. It doesn't have to be all caps, but whatever you typed here, we're going to use again. So if you had delta notch in lowercase here, it would be delta notch here. The cell type name has to be in all caps. Okay. NumPy, I believe, is now loaded by default in CompuCell under the name NP. And so if you want a random number, you can use np.random.uniform, minimum and maximum value. You get a random number. And we're going to add this to the step function. And I'll show you what the code could look like. In the start function, we've added the antimony to cell type A, in our case. If you gave the cell a different name, cell A would be whatever you used. In this case, I've named the model DN, and then for cell in self.celllist, cell.spml.dn, Fuse gave it a different name, that would be different. Quote D equals np.random uniform between 0.9 and 1. Now, your self.celllist here will also be specifying the initial volume, the target volume and the lambda volume for the cell. So you may have some additional code. This is the added code. And then in the step function, add self.timestep_spml. Run that and see what it does. Make sure it doesn't crash. there's a statement 0.5 and 0.5 for initial values of D and N were placeholders. That's exactly right. Yes. The next step is going to be doing exactly what you say, which is to, the question was, do we need to set the value of D average? And that's the last thing we're going to do, yes. And so I'd like to be able to walk through all of this with you step by step, but we're going to run out of time. And so if you're able to keep up, that's good. If not, please open that completed exercise and we'll look at the code while we're going through this together. Okay. The next thing we're going to do is we're going to loop over all the cells in the step function. We're going to create a placeholder for the average value of D. We're going to iterate over the neighbors of the cell. You have to check if neighbor to make sure it's not medium. This is a slight annoyance in CompuCell. Read the delta level for each cell, add the value of delta from the neighboring cell to my current cell, count how many neighbors I had, normalize by the number of neighbors, and update the value of D average inside my cell. If we wanted to be a little fancier, we would weight the signal by the contact area, not just by whether we're contact with a cell or not, but by the contact area between the two cells, which is more biologically realistic. All right, let's see how that looks. We already had neighbor tracker turned on. We need it. When we're iterating over neighbors, we use that Python visit to say visit neighbors. And so what we're going to do, one thing about visit neighbors is maybe unfamiliar if you're not Pythonic, is it doesn't just return the neighbors, it returns a pair, which is the neighbor and the common surface area. That's a little bit, it's convenient, but it's a little bit unusual from programming languages. Python will have something, we're used to on the left-hand side of an equal sign to have one thing. In Python, you can have a list of things on the left-hand side of an equal sign because you can return complex objects. So in our step function, for cell in self.cell list, average contact is 0, number of contacts, number of neighbors is 0. And now I use the iterator visit neighbors for neighbor, common surface area in self.get cell neighbor data list that we boilerplate in from the Twit. And then we have to do if neighbor, because the medium doesn't have, there isn't any medium in this, so we should be okay. But if there were medium, we'd have a problem. Average, oh, sorry, this has got the common surface area one, so I apologize. This is actually not the slide I wanted. Let's see, do I have it? Here it is. So here, in step for cell in self.cell list, the average is 0, number of neighbors is 0. I had the answer for the harder problem first, and I apologize for that. For neighbor, common surface area in self.neighbor cell list, cell, if neighbor, D average equals neighbor.sbml.dn of D, number of neighbors plus equals 1. If there are any neighbors, update the value in my cell, D average divided by number of neighbors. This looks like a lot of typing, but quite a bit of it is templated in the Twit code snippets. Again, after each one of these steps, you want to check to make sure things run. So if you've got a typo, these steps are designed so that they're independent, so that if you run it, it may not display anything interesting, but it shouldn't crash. So you can either use the code that Julio pasted in the chat or type it yourself. And I want to go to the last step, which is now that we've got the calculation of D and N, we need to display them. And we're going to create tracking fields. We've seen tracking fields before. the tracking field has to go in the initialization after the underscore init, before the steppable declaration. If you put it above the underscore init, it will crash. Actually, it will not crash, it just won't display. If you try to put it inside of the steppables, it won't work. Again, add tracking field add auxiliary field automatic tracking is in the code snippets. That's important. And then in the step function, you have to copy from cell.sbml.dn to cell dict of n, and the same for D. And that is the code that Gopal pasted in the chat. Again, if you don't remember how to do the tracking field, let me just pull up the tracking field one, because that I had meant to paste in here in this slide a reminder of how to find the tracking fields in Twit. Let me do that with you. So here we have the init here. After the init is here, def init steppable base pi. We put the tracking field definitions here, like that. And if we don't remember where those come from, and I don't know, tell me if the pull down menu shows. Does the pull down menu show? Yes, good. So we go to extra fields, automatic tracking, track scalar attribute. And that will give us the text we need here. We give the field a name. We type the variable name here. And then we have to go down where we calculated diav. And here we have to copy to cell dictionary from cell.sbml.dn the value of D and the value of N, because only the cell dictionary entries are displayed with the tracking fields. So again, you're adding the tracking fields here in lines 9 and 10, and you're copying the values from the SBML dictionaries to the cell dictionaries in lines 48 and 49. And try that and see if it runs. If you're having trouble doing it yourself, use the exercise code and run it yourself. Okay, so this is the code that I just showed you. In lines 9 and 10, you put the track field. In lines 48 and 49, you copy the dictionary entries from the SBML model into the cell dictionaries. And that completes the exercise. And Gopal, and the one thing you're going to have to do now is when you run it, you're going to have to display the delta and the notch fields instead of the cell fields. Okay. So see what people can do. Again, if you can't follow along in the speed we've got, run the exercise from the download. Is there a programmatic way to make it display tracking field windows? So in principle, you can save the player state. In practice, the player state saving is a little bit dodgy. I would like to see an extension to CompuCell where we can actually display save the player state in a more convenient way. It depends on how you exit the code, whether the player state is saved or not. But in general, you may have to set up the display every time. That would be a great extension for CompuCell, Sharon, if you want to write it. Okay, it looks like people are getting it. This is what the simulation looks like. That this is running the downloaded code that I gave you here. And this is what I have. The downloaded code should do it. the link for the slides was shared. It's always the same link. Yeah, it looks like you've got it. Looks like you maybe didn't fill the whole space with cells, but that's interesting too when you have medium in contact with the cells. You should have seen something look like this. If you were having trouble with it again, go back to that download exercise. I am not going to have time to talk about steering panels. This particular exercise is a nice one to use steering panels with. I strongly recommend looking at the slide deck to see how to use steering panels to change the parameters. And you can do that as a little homework exercise. Another way to do a homework exercise is to have the growth rate of the cells. You can start with a single cell running this model, have it grow and divide, and see how the pattern evolves. That's available to you. You can have the growth rate depend on the notch or the delta level, which is biologically meaningful. And that's also quite interesting. And you can do notch as a promoter of cell growth, for example. And that's also available to you. And it's also interesting to use a fixed geometry, which is something that you get in particular cell initial configurations for biological systems like the growth of vasculature. And you can see how delta notch works in that context. So I apologize if we had to rush a little bit here. I do encourage people to go back to the slide decks and the videos and downloadable exercises. And I'm going to stop here and do the module completion poll. Okay, I realize that went a little bit fast, and there's a lot to do here, but you'll get plenty of experience. The best thing to do with this kind of thing, this kind of learning experience, is to look at the code. I've explained what each component of the code does. There are not that many lines per step. And so walk through it and then see whether you can make small changes to it. You could make display different functions. You could update the values of the parameters in particular ways. You could weight the signal between cells by the contact area and so on. So I'd suggest that if you weren't able to follow all the steps in detail, you go back over it in the slide deck and try working it through. Yes, people, Julio and Vikram say, well, does the pattern stabilize or not? And that's very interesting. It depends on the geometry. And it depends on the parameter values. If we did the steering example where we changed the parameter values of the simulation as it runs, we could switch it from delta and notch being in phase to being out of phase, from delta and notch achieving stable states to being oscillatory or not patterning at all. And we can also, by changing the number of neighbors of the cells, we can change whether we get, and the size of the lattice, we can change whether we get a stable pattern or not.